So when we're not at standard conditions, meaning when our temperature, let's go ahead, when our temperature is not 298 K, when we're not at a pressure of 1 atm, or when we're not in a 1 molar solution of our own ions, we're going to have to invoke the Nernst equation. So we're going to have to look at and analyze this from a thermodynamic perspective. So if we look at the definition of electrochemical work, it is going to be equal to basically Q charge times your voltage, or your cell voltage, which is just simply minus N, which is the number of moles of electrons, Faraday's constant, and Faraday's constant is equal to 96485. So Faraday's constant, we should kind of remember from, hopefully, physics, probably E and M. I can't remember. Let me see. What's the, what should be, and that should be in coulombs. So Faraday's constant, and then times your cell voltage in volts. And you can kind of see that here as well. So we've been calculating everything in the standard condition. And one thing you could notice is the change in free energy. If our E naught is positive, that is going to be a spontaneous reaction. So if our E naught is negative, it's not going to want to flow essentially in that opposite direction in terms of our electrons. But that's a little bit beyond the point. But we can relate this back to our kind of fundamental expression. Oops, my pen is not cooperating. So let me plug that in quickly. Sorry, I'm maybe slightly away. There we go. Let me charge my pen soon. All right, good. So we can rewrite the reaction in terms of that change in chemical potential, or basically for a chemical reaction. So we can look at this and we can say the natural log of the arithmetic products and some of the reactants and products. So we can rewrite it here. And eventually we will get to an expression here where the change in, this is the cell voltage at non-standard conditions. E naught is my standard cell conditions. R is my Gibbs free energy, or excuse me, my gas constant, 8.314 joules per mole K. NF, Faraday's constant. And here, instead of writing it like this and like this, let's look at how this was done. So this was assuming that our full cell reaction was the following. So we were looking at copper 2 plus Fe goes to Fe 2 plus Cu. So when I'm writing out this natural log of products over reactants, so I'm going to look at concentration, because activity is basically proportional to concentration. So I'm going to take the concentration of my products, which is Fe 2 plus concentration of Cu over, I have a little bit of cold today, Cu2 plus concentration times Fe, so products over reactants. Now, if I'm pure material, my concentration is going to be 1 mole. So these automatically cancel out. So this would be concentration of products over concentration of reactants, and that's how you're going to solve for problems with the Nernst equation. So your E naught would be if we were at, and one of the cool things is, at standard conditions, what are the concentrations of these ions? 1, 1. What's natural log of 1? So the natural log would be of 1 is 0, so all this is, disappears, and my E would be equal to E naught. So it's a beautiful expression because it has built in if we're at standard conditions. But if not, I can solve for any of these variables. And one of the cool things is you can see I can actually, let's say my E naught is positive. Excuse me. I think I'm getting a little bit of a cold. Let's say my E naught is positive. I can actually change temperature or kind of the concentration of these products and reactants to actually make the E that I measure negative. So that's one of the kind of cool things that we will investigate and see in these problems. So we'll see you all in the next video where we try to think about ways we can protect against corrosion. So see you then. Thanks. Bye.